The Milky Way is not large. That statement alone should stop you cold. The galaxy you were born in, the galaxy that contains every civilization humanity has ever imagined, every star visible to the naked eye from any point on Earth, every planet we have ever photographed, all of it fits inside a structure so ordinary by the standards of the observable universe that astronomers classify it as a mid-sized spiral. Nothing special, a common configuration. One of perhaps 2 trillion galaxies distributed across the observable universe, most of which we will never reach, never image in detail, never truly understand in a single human lifetime. Now hold that thought, because there are galaxies out there that make the Milky Way look like a suburb. The Milky Way spans roughly 100,000 light-years in diameter. A light-year is the distance light travels in 1 year, moving at 300,000 kilometers per second, the absolute speed limit of the universe. In 1 second, light covers a distance equal to circling the Earth 7.5 times. In 1 year, it covers approximately 9.5 trillion kilometers. The Milky Way, at 100,000 light-years across, is therefore roughly 950 quadrillion kilometers wide. If you launched a spacecraft from one edge of our galaxy at the speed of the fastest human-made object ever built, the Parker Solar Probe, which reached approximately 690,000 kilometers per hour at its closest approach to the Sun, it would take you approximately 160 million years to cross from one side to the other. That is longer than the entire Mesozoic era, longer than the reign of the dinosaurs. And again, that is the ordinary galaxy, the unremarkable one. There exist structures in the universe, confirmed, observed, cataloged by telescopes, whose diameters stretch to 6 million light-years, to 10 million. Some candidates push beyond that. These are not theoretical constructs. These are not artifacts of bad data or wishful extrapolation. They are real objects, gravitationally bound systems of stars, gas, dust, dark matter, and plasma, sitting in the darkness of deep space, and they are so incomprehensibly large that the physics governing their formation challenge nearly every assumption cosmologists had built over the previous century. What are these things? How did they form? What happens inside them? And what does their existence tell us about the nature of the universe itself? Galaxies, at their most fundamental level, are gravitationally bound collections of stars, gas, dust, and dark matter, all orbiting a common center of mass. The Milky Way contains an estimated 200 to 400 billion stars. It also contains a supermassive black hole at its core, Sagittarius A star, with a mass approximately 4 million times that of our Sun. This black hole is massive by any human standard. By the standards of the largest galaxies in the known universe, it is a footnote. The universe is approximately 13.8 billion years old. In the earliest fractions of its existence, in the first few hundred million years after the Big Bang, matter was not distributed in the smooth, uniform way many people assume. The Big Bang did not produce a perfectly homogeneous cloud of hydrogen and helium that simply expanded outward at equal density in all directions. Quantum fluctuations in the first fractions of a second after the singularity, variations in energy density so small they existed at the subatomic scale, were stretched by the rapid expansion of space itself into large-scale structures. These fluctuations became the seeds of everything. Regions that were fractionally denser than their surroundings began to gravitationally attract more matter. Over hundreds of millions of years, these regions collapsed into the first stars, then the first galaxies. But gravity does not stop at the borders of a single galaxy. Galaxies attract other galaxies. They form groups. Groups merge. They form clusters. Clusters aggregate into superclusters. And at the very top of this hierarchy of cosmic structure sit the giants, the brightest cluster galaxies, the CD galaxies, the elliptical behemoths that squat at the gravitational centers of the largest galaxy clusters in the observable universe, having consumed their neighbors over billions of years of relentless cosmic cannibalism. This is not metaphor. Galaxy mergers are among the most thoroughly documented processes in observational astronomy. The Hubble Space Telescope has imaged thousands of them at various stages. The Milky Way itself is on a collision course with the Andromeda Galaxy, Messier 31, and the two will begin to merge in approximately 4.5 billion years. The result will be a single, larger elliptical galaxy, informally nicknamed Milkometa by some researchers. What we observe in the largest galaxies in the universe is this same process carried to its logical extreme, repeated dozens or hundreds of times over the course of cosmic history. Consider IC 1101. For years, it held the title of the largest known galaxy, a title contested and refined as telescope technology improved, but never truly stripped. IC 1101 is a supergiant elliptical galaxy located approximately 1 billion light-years from Earth, sitting at the center of the galaxy cluster Abell 2029. Its diameter is estimated at approximately 6 million light-years. That is 60 times the diameter of the Milky Way. If IC 1101 were placed at the center of our own galaxy's position, its outer edges would extend well beyond the Andromeda Galaxy, past the Triangulum Galaxy, consuming dozens of members of our local group entirely. The entirety of what we call our cosmic neighborhood, every galaxy we have ever named, every star we can see with any telescope pointed at the local sky, would fit comfortably inside it with room to spare. IC 1101 contains an estimated 100 trillion stars. 100 trillion. The Milky Way, at its upper estimate, contains perhaps 400 billion. That means IC 1101 contains roughly 250 times more stars than our entire galaxy. Its central black hole, a supermassive black hole powering what was once an active galactic nucleus, carries a mass estimated at approximately 40 billion solar masses. 40 billion times the mass of our Sun, compressed into a single gravitational singularity. Sagittarius A star, the black hole at the center of our own galaxy, masses at 4 million solar masses. The black hole at the heart of IC 1101 is 10,000 times more massive. These numbers stop being intuitive very quickly. This is by design. The universe was not engineered for human comprehension. But the comparison is worth dwelling on. If Sagittarius A star were a golf ball, the central black hole of IC 1101 would be a sphere roughly 21 meters in diameter. Not the golf course, the sphere itself. There is a common misconception worth dismantling directly. Many people assume that larger galaxies simply contain proportionally more of the same types of stars and structures as our own Milky Way, that a galaxy 6 times larger would just be a scaled-up spiral with more of everything. This is wrong. The largest galaxies in the universe are almost universally elliptical in shape, not spiral. They have lost the organized rotational structure that defines galaxies like the Milky Way or Andromeda. There are no grand spiral arms, no disk, no distinct plane of rotation. Instead, these galaxies are smooth, featureless, diffuse clouds of mostly older stars, their angular momentum averaged out and dissipated across billions of years of repeated mergers. When two spiral galaxies collide, their organized rotation patterns disrupt each other. Gas clouds collapse, triggering brief but intense bursts of star formation. Then the turbulence settles. What remains is an elliptical. The larger the elliptical, the more mergers it has survived. IC 1101 is the product of an almost unimaginable merger history. Its outer halo of stars, a diffuse, ghostly shell extending far beyond its bright central core, is the accumulated debris of hundreds of smaller galaxies it has gravitationally stripped and absorbed. Astronomers call these stellar halos, and they are written records of cannibalism, readable by anyone with a sufficiently sensitive telescope and the patience to interpret the data. The chemistry of the stars in these halos, their ages, their orbital patterns, all of it traces back to the galaxies they once belonged to, galaxies that no longer exist as independent structures. And IC 1101 is not alone. It is not even definitively the largest. In 2015, astronomers analyzing data from a combination of ground-based telescopes and archival survey data confirmed the full extent of a structure that had been partially known for decades, but never properly measured. What they found would reframe every conversation about galactic scale, and raise a question that cosmologists are still working to fully answer. The question is not just how large galaxies can grow. The question is whether there is any upper limit at all. For most of human history, the night sky was simply the night sky, a ceiling, A fixed dome of light, permanent and unchanging, whose only movements were the predictable arcs of planets and the seasonal drift of constellations. The idea that those faint smudges of light visible between the stars, the ones that no telescope of the 18th century could resolve into individual points, might themselves be entire galaxies, entire systems of hundreds of billions of stars located at distances so extreme they made the mind revolt, was not a scientific fact. It was a philosophical debate. And for a surprisingly long time, the scientific establishment got it wrong. The objects in question were called nebulae. The word is Latin for clouds, which is exactly what they looked like through the lenses and mirrors available to astronomers before the 20th century. Soft, diffuse, unresolved patches of faint luminosity scattered across the sky. Some of them, like the Orion Nebula, were indeed clouds, vast regions of interstellar gas and dust within the Milky Way itself, lit from within by newborn stars. But others, the ones with faintly discernible spiral or elliptical structure, were something else entirely. They were not clouds within our galaxy. They were other galaxies, entire universes of stars, gas, and dark matter separated from us by distances that dwarfed anything in the known astronomical catalog. The debate over their true nature reached its peak in April of 1920 in what became known as the Great Debate, a formal scientific exchange held at the Smithsonian Institution in Washington between astronomers Harlow Shapley and Heber Curtis. Shapley argued that the spiral nebulae were structures within the Milky Way and that our galaxy constituted essentially the entirety of the visible universe. Curtis argued the opposite, that these nebulae were independent star systems, comparable in scale to our own galaxy, located at enormous distances. The measurement tools of the era were simply not precise enough to settle the question definitively that night. What settled it, 4 years later, was a photograph. In 1924, Edwin Hubble, working with the 100-inch Hooker telescope at Mount Wilson Observatory in California, at the time the most powerful optical telescope on Earth, resolved individual stars within the Andromeda Nebula. Among them, he identified a specific type of variable star known as a Cepheid. Cepheids pulse with a period directly related to their intrinsic luminosity. The longer the pulse, the more intrinsically bright the star. By measuring how bright Andromeda's Cepheids appeared versus how bright they actually were, Hubble calculated a distance. His initial estimate placed Andromeda at approximately 900,000 light-years away, well outside any possible boundary of the Milky Way, even under the most generous estimates of our galaxy's size. Curtis had been right. The spiral nebulae were not clouds. They were island universes. The cosmos was not one galaxy. It was 2 trillion of them. That recalibration of scale, that single observational result from a photographic plate in the mountains above Los Angeles, is arguably the most consequential shift in human cosmological understanding since Copernicus removed the Earth from the center of the solar system. It did not merely expand the known universe. It revealed that the known universe had been wrong by a factor that beggars comprehension. Everything humanity had ever assumed about the boundaries of existence was off by orders of magnitude. And yet, even after Hubble's discovery, the question of how large individual galaxies could grow remained largely unasked. For decades, the community focused on mapping the distribution of galaxies across space, measuring their recession velocities, building the framework of modern cosmology. The size hierarchy within the galaxy population itself, the question of what sat at the very top, what occupied the position of absolute maximum, was a problem that required instruments and survey techniques that would not exist until the latter half of the 20th century. What those instruments eventually found was a class of objects that had been hiding in plain sight, sitting at the gravitational centers of the universe's most massive galaxy clusters, so enormous they had effectively been mistaken for the clusters themselves. They are called brightest cluster galaxies, or BCGs. They sit at the bottom of the deepest gravitational wells in the observable universe. They are surrounded by hundreds, sometimes thousands of smaller companion galaxies. And they have been feeding, slowly, continuously, relentlessly, for billions of years. The mechanism is not explosive. It is not dramatic on human timescales. It is gravitational accretion, the steady infall of smaller galaxies that stray too close to the gravitational potential of the central giant. A dwarf galaxy orbiting the outskirts of a massive cluster loses orbital energy through tidal interactions and dynamical friction, a process in which the gravitational wake left behind by a moving body through a sea of surrounding matter gradually bleeds away its momentum. Over hundreds of millions of years, the dwarf spirals inward. Its outer stars are stripped away first, feeding the outer stellar halo of the BCG. Eventually, what remains of its core sinks toward the center and merges. The BCG grows by a small but measurable amount. Then the process begins again with the next victim. Multiply this by hundreds of merger events across 10 billion years of cosmic history, and you arrive at IC 1101. You arrive at the Phoenix Cluster's central galaxy, whose diameter reaches 2.2 million light-years. You arrive at NGC 4889 in the Coma Cluster, stretching 1.3 million light-years across. These are not anomalies. They are the expected end products of a process that cosmologists had theorized but underestimated in its cumulative power. The Coma Cluster itself is instructive. Located approximately 320 million light-years from Earth, the Coma Cluster contains over 1,000 confirmed member galaxies, within a region roughly 20 million light-years in diameter. At its center sit two massive elliptical galaxies, NGC 4889 and NGC 4874, locked in a slow gravitational embrace, their stellar halos already beginning to merge. What astronomers observe in the Coma Cluster today is a snapshot of a process that is still ongoing. The cluster has not finished assembling. The central galaxies have not finished growing. In another few billion years, what are now two distinct objects will likely be one, larger, smoother, more diffuse, and more dominant than either is today. This is not a rare configuration. Galaxy clusters are, by definition, environments of gravitational competition, where the most massive object at the center has an inherent and compounding advantage. Mass attracts mass. The larger the central galaxy grows, the more effectively it captures infalling material. Cosmologists describe this as hierarchical structure formation. The universe builds complexity from the bottom up, with small structures forming first and merging progressively into larger ones. The BCGs at the centers of massive clusters represent the terminal stage of this hierarchy, at least for baryonic matter. The ordinary matter made of protons, neutrons, and electrons that constitutes every star, planet, and living thing we have ever observed. Dark matter complicates this picture enormously. The stellar mass of even the largest known galaxies accounts for only a fraction of their total gravitational mass. IC 1101 stellar content, that extraordinary 100 trillion stars, exists inside a dark matter halo whose total mass dwarfs the stellar component by a factor estimated between 5 and 10. The dark matter halo of a massive BCG can extend for several million light-years beyond the visible edge of the galaxy, an invisible gravitational scaffolding that the luminous stars merely trace. When astronomers measure the size of these galaxies, they are almost always measuring the extent of the stellar component, the light. The true gravitational footprint of the object is far larger and far less precisely constrained. This distinction matters because it shapes the question of how these galaxies grow. Stars merge when galaxies collide. Dark matter halos interpenetrate, overlap, and blend in ways that stars almost never do, because stars, despite their enormous size relative to human experience, are vanishingly small relative to the distances between them. Two galaxies can pass through each other with virtually no stellar collisions. What binds them, what pulls them back together for a second and third pass until they finally merge, is the gravity of their dark matter halos interacting across millions of light-years of space. It is that invisible architecture, the dark matter framework, that determines which galaxies grow to become the giants of the observable universe, and which ones remain small, tidally disrupted, and eventually consumed. The luminous galaxies we photograph and catalog are, in a meaningful physical sense, the surface of something much deeper. The visible tip of a dark iceberg whose full dimensions we are only beginning to measure. Now consider what happens when a galaxy cluster, not just a single galaxy, but an entire cluster containing hundreds of galaxies and trillions of solar masses of hot gas and dark matter, collides with another cluster of comparable mass. The energy involved makes the merger of two individual galaxies look trivial. And in the observational record, the evidence of exactly these events is everywhere, written in the X-ray emission of shocked intergalactic gas, in the displaced distributions of dark matter mapped through gravitational lensing, in the disturbed morphologies of BCGs caught mid-merger. Some of the largest single-object structures in the observable universe bear the unmistakable scars of cluster-scale collisions that occurred billions of years ago. The Bullet Cluster, formerly known as 1E0657-556, is the most famous example. Located approximately 3.7 billion light-years from Earth, it shows two galaxy clusters in the aftermath of a high-velocity collision. The hot gas of both clusters, visible in X-ray, was slowed and distorted by the collision. The dark matter halos, detectable only through gravitational lensing, passed through each other almost without interaction. The result is a system where the luminous gas and the dark matter are spatially offset from each other. Direct observational proof that dark matter is a physically real component of these structures, not merely a mathematical correction to gravitational theory. Within these collision environments, BCGs are not passive passengers. They accrete material from the shocked gas, from disrupted satellite galaxies, from the debris fields of ongoing mergers. They are the beneficiaries of every violent event in the history of their host cluster. And the most massive clusters in the observable universe, the ones that have undergone the most mergers, accumulated the most mass, and sat at the deepest gravitational potential wells for the longest periods, produce the most extreme BCGs, the ones whose diameters enter the range of multiple millions of light-years, the ones that force a revision of what the word galaxy is even capable of meaning. That revision, when it fully arrived, came not from a single dramatic announcement, but from a slow accumulation of data across multiple observatories and multiple decades. And it raised a question that the standard model of galaxy formation had not fully anticipated. How do you build something that large in the time the universe has been running? The universe is 13.8 billion years old. That number is not an estimate in the colloquial sense. It is a measurement, derived from multiple independent lines of evidence, cross-checked against the cosmic microwave background radiation, against the observed expansion rate of space, against the age distributions of the oldest stars in the oldest globular clusters. 13.8 billion years is how long the universe has had to build everything we observe. Every galaxy, every cluster, every filament of the cosmic web, every supermassive black hole at the center of every BCG, all of it assembled within that single window of time. The problem is that 13.8 billion years is not as long as it sounds, not when you were trying to build a galaxy 6 million light-years across. Galaxy formation did not begin at the Big Bang. The first few 100,000 years of the universe's existence were too hot and too dense for neutral atoms to even form. The plasma filling all of space was opaque. Photons could not travel freely because they were constantly scattering off free electrons. Then, at approximately 380,000 years after the Big Bang, the universe cooled to the point where protons and electrons could combine into neutral hydrogen. The photons, suddenly free, streamed outward in all directions. Those photons are still traveling today. We detect them as the cosmic microwave background, a faint, uniform glow of microwave radiation permeating every direction of the sky, carrying an imprint of the universe's structure at that precise early moment, its temperature varying by only tiny fractions of a degree from point to point across the sky. Those tiny temperature variations, measured by satellites including COBE, WMAP, and the Planck Observatory, are the fossilized fingerprints of the quantum fluctuations that seeded all large-scale structure. Regions that were fractionally overdense in the early plasma correspond to regions of slightly higher temperature in the microwave background. And those same regions, followed forward through cosmic time using computational simulations, correspond to the locations of galaxy clusters and cosmic filaments in the universe today. The match between observation and simulation is one of the great confirmatory achievements of modern cosmology. The physics works, the seeds were real, and the structures they grew into are exactly as large as the math predicts. Almost. The first stars ignited somewhere between 100 million and 200 million years after the Big Bang, in dense pockets of collapsing hydrogen gas. They were not like the sun. They were enormous, hundreds of times more massive. and they burned through their fuel in only a few million years before exploding as supernovae, seeding the surrounding gas with the first heavy elements the universe had ever produced. The first galaxies assembled around the same time, small and irregular and intensely star-forming. Nothing like the grand spirals and smooth ellipticals that dominate the present-day universe. The growth from those early dwarf proto-galaxies to the giants we observe today is governed by a process cosmologists call hierarchical merging. Small structures form first. Then they merge into progressively larger structures over time. This is a firm prediction of the lambda CDM model, the standard model of cosmology, which incorporates dark energy and cold dark matter as its two major components beyond ordinary baryonic matter. In lambda CDM, the universe's matter is dominated by cold dark matter, particles that interact gravitationally but not electromagnetically, invisible to telescopes, moving slowly relative to the speed of light. Cold dark matter clumps early and efficiently into halos of varying mass, and those halos provide the gravitational scaffolding within which galaxies form and grow. The mass function of dark matter halos, the distribution of how many halos of each mass exist at any given time, is a steep power law. There are enormous numbers of small halos, there are very few massive ones. And at the very top of the distribution, the most massive halos in the observable universe, the formation of which requires the merging of dozens of intermediate mass halos over billions of years, sit the galaxy clusters, and at their centers, the BCGs. What makes the largest BCGs scientifically remarkable is precisely the tension between their observed sizes and the predictions of standard hierarchical models. Lambda CDM does predict the existence of giant elliptical galaxies at cluster centers. What it did not initially predict, or predict with sufficient precision, was how extended the stellar halos of these objects would be. The observed stellar mass in the outer regions of the most massive BCGs, particularly the diffuse intracluster light that surrounds them, a faint, spread-out glow of stars that have been tidally stripped from infalling galaxies and now orbit the cluster potential rather than any individual galaxy, is in some cases larger than theorists expected. Intracluster light is one of the most scientifically rich and observationally challenging phenomena in extragalactic astronomy. It is faint, typically only 1% as bright as the night sky background, which makes it extraordinarily difficult to detect and quantify from ground-based telescopes. It is diffuse, spread across regions millions of light-years in extent. And it is ancient. The stars composing it are predominantly old, metal-poor red giant stars, stripped from dwarf galaxies and low-mass spirals during the early assembly phases of their host clusters. When the James Webb Space Telescope and large ground-based surveys like the Dark Energy Survey began pushing the sensitivity limits of intracluster light detection, what emerged was a picture of BCGs embedded in stellar envelopes far more extended than their bright central cores suggested. The galaxy, in the traditional photometric sense, grades seamlessly into the cluster's diffuse stellar component over distances of millions of light-years. The boundary between where the galaxy ends and the cluster begins is not a physical edge. It is a measurement convention. This has direct implications for how we define the size of the largest galaxies. When astronomers report that IC 1101 spans 6 million light-years, they are typically including the extended stellar halo detected at very low surface brightness levels. Under stricter definitions, limiting the measurement to regions above a specific surface brightness threshold, the number changes. Different papers report different values depending on the detection method, the telescope sensitivity, and the surface brightness limit applied. This is not sloppy science. It is the honest confrontation with the fact that these objects have no clean outer boundary. They are not hard-edged structures. They are density gradients, regions where the concentration of stars and dark matter exceeds the surrounding intergalactic medium, fading asymptotically toward zero. The physics governing the inner regions of these galaxies is no less extreme. At the centers of the most massive BCGs sit the most massive black holes yet measured. The relationship between black hole mass and the stellar mass of the host galaxy's central bulge, known as the M-sigma relation, is one of the most robust empirical correlations in extragalactic astronomy. More massive galaxies harbor more massive black holes. This relationship holds across many orders of magnitude in galaxy mass. Its existence implies that the growth of central black holes and the growth of their host galaxies are not independent processes. They regulate each other through a feedback mechanism whose precise physics remains an active research question. In the case of the most massive BCGs, the feedback mechanism is dramatic and observable. The supermassive black holes at their centers, when they are actively accreting material from the hot intracluster gas, launch relativistic jets, highly collimated streams of plasma accelerated to near the speed of light, extending for hundreds of thousands of light-years in some cases, and in the most powerful examples, for millions of light-years beyond the host galaxy into the surrounding intracluster medium. These jets excavate enormous cavities in the hot X-ray emitting gas of the cluster, inflating bubbles of relativistic plasma that rise buoyantly through the intracluster medium, like bubbles rising through water. Though the fluid in this case is a plasma at temperatures of tens of millions of degrees. The Perseus cluster, located approximately 240 million light-years from Earth, is the best studied example of this AGN feedback process. At its center sits NGC 1275, a massive elliptical galaxy harboring a supermassive black hole that drives one of the most powerful active galactic nuclei known. The Chandra X-ray Observatory has imaged the Perseus cluster's hot gas with extraordinary detail, revealing a set of concentric ripples, actual sound waves, propagating outward through the intracluster medium from the periodic outbursts of the central AGN. The frequency of those sound waves corresponds to a B-flat note approximately 57 octaves below middle C, far below the threshold of human hearing, with a period of roughly 10 million years per oscillation. The cluster is, in a precise physical sense, ringing. The energy source is the black hole at the center of the BCG. This feedback process is not merely aesthetically striking. It is cosmologically essential. Without AGN feedback, the cooling of the hot intracluster gas, which radiates energy as X-rays and slowly loses thermal pressure, would cause it to collapse inward toward the cluster center, triggering runaway star formation at rates orders of magnitude higher than observed. The BCG at the center would grow far faster than it does. The most massive galaxies in the universe would be even more massive than they already are. AGN feedback is the thermostat that regulates the growth of the universe's largest structures, a self-limiting mechanism in which the very black hole whose mass was built by the galaxy's growth also acts as a brake on that growth. The Abell 2029 cluster, home to IC 1101, shows evidence of this regulatory mechanism operating across cosmic time. The cluster's X-ray surface brightness profile, a fingerprint of the hot gas distribution, shows the signatures of multiple AGN outburst events at different epochs, each one depositing energy into the intracluster medium, each one temporarily suppressing the cooling flow, each one subtly reshaping the environment in which the BCG sits. IC 1101's black hole, estimated at 40 billion solar masses, did not reach that mass passively. It grew through the same accretion and merger processes that built the galaxy around it, and it has, in turn, shaped the cluster environment through which that galaxy has continued to grow. The largest galaxies in the universe are not static objects. They are not finished products sitting inertly in the darkness. They are dynamic systems, actively accreting, actively being regulated, embedded in environments of hot gas and dark matter that extend for tens of millions of light-years in every direction. Their current size is not their final size. In the far future, tens of billions of years from now, as the expansion of the universe accelerates under the influence of dark energy and the population of galaxies within each cluster becomes increasingly isolated from those in other clusters, the BCGs will continue to cannibalize their immediate neighbors, growing slowly larger in an increasingly empty universe. The trajectory of their growth is set by the physics of their environment, but the upper limit of that growth, whether any physical process exists that definitively caps the size of a galaxy, is a question that the data, as of the early 21st century, had not fully answered. In 2015, a team of astronomers announced the complete characterization of an object that had been partially cataloged for decades, but never fully measured. What they found did not merely challenge the existing record. It challenged the timeline by which structures of such extraordinary scale were even supposed to exist. In 2015, a paper published in the monthly notices of the Royal Astronomical Society by a team led by researcher Massive Collapse of Structure, redefined what the observational community understood about the upper boundary of galaxy size. The object in question was Alcyonius, not yet named at that point, not yet fully characterized, but partially catalogued in earlier radio surveys as an extended radio galaxy of unusual scale. The full measurement of its true extent would require combining data from multiple radio telescope arrays across different epochs, cross-referencing with optical and infrared imaging, and applying careful subtraction techniques to isolate the galaxy's emission from background contamination. When the final numbers were assembled, what emerged was a structure that exceeded every prior record by a margin that initially prompted the team to recheck their data. Alcyonius. The name comes from Greek mythology, a giant son of Uranus, considered the greatest of the Gigantes. The astronomers who formally published its full characterization in 2022 in the journal Astronomy and Astrophysics, led by Martijn Oé and colleagues at Leiden University, chose the name deliberately. The object earned it. Alcyonius is a giant radio galaxy. Located approximately 3 billion light-years from Earth, it is not merely a large elliptical galaxy in the traditional sense. It is a radio galaxy, a class of active galactic nuclei in which the central supermassive black hole drives relativistic jets that extend far beyond the visible stellar body of the host galaxy, radiating at radio wavelengths through a process called synchrotron radiation. Charged particles, primarily electrons, are accelerated to near the speed of light within the jet, and as they spiral around magnetic field lines, they emit radiation across a broad spectrum, with radio frequencies dominating at large distances from the nucleus. The jets of Alcyonius extend in two directions from the host galaxy's nucleus. End to end, the full extent of its radio lobes, the diffuse regions of synchrotron plasma where the jets terminate and spread outward into the surrounding intergalactic medium, reaches a measured distance of approximately 16.3 million light-years. 16.3 million light-years, end to end. The Milky Way, at 100,000 light-years across, would fit inside Alcyonius approximately 163 times in a single straight line. If you placed Alcyonius at the position of the Milky Way's center, one lobe would extend past the Andromeda Galaxy, past the Triangulum Galaxy, past the entirety of the local group, and continue outward into the void separating us from the next nearest galaxy cluster. The other lobe would extend an equivalent distance in the opposite direction. The entire structure would envelope a volume of intergalactic space so large that most of the galaxy clusters visible in a typical deep-field image would fit comfortably within it. The host galaxy of Alcyonius, the actual stellar body at the center of this radio structure, is itself a massive elliptical galaxy, but by BCG standards it is not the most massive object known. Its stellar mass is estimated at approximately 2.4 times 10 to the 11th solar masses, large, but not record-breaking. Its central black hole mass is estimated at approximately 300 million to 400 million solar masses, which is substantial but again not the largest known. What makes Alcyonius extraordinary is not the mass of its central engine, it is the environment in which that engine operates. The OE team's analysis revealed something that the observational community had not anticipated from a record-breaking radio galaxy. Alcyonius sits in one of the least dense intergalactic environments yet documented for a giant radio galaxy. Most giant radio galaxies of extreme scale are embedded in galaxy clusters, environments where the dense intracluster medium provides resistance against which the jets interact, creating the characteristic lobes and hotspots seen in radio galaxy morphology. Alcyonius, by contrast, appears to sit in a region of the cosmic web characterized by unusually low intergalactic medium density. The jets have been able to propagate outward with minimal resistance. There is almost nothing in the surrounding space to stop them. This finding inverted a long-standing assumption in radio galaxy physics. For decades, the prevailing expectation was that the most extended radio galaxies would be found in the densest environments, that the richness of material available for the black hole to accrete would produce the most powerful jets, and those powerful jets would push the radio lobes to the greatest distances. Alcyonius demonstrated the opposite. A moderately powered jet operating over a sufficiently long period in a sufficiently underdense environment can produce a structure that dwarfs anything generated by a more powerful engine constrained by a dense surrounding medium. Scale, in this case, is as much a product of emptiness as of power. The implications reach beyond radio galaxy physics into the broader question of how galaxies interact with the large-scale structure of the universe. The cosmic web, the network of filaments, sheets, voids, and nodes that constitutes the large-scale distribution of matter in the universe, is not uniform. The filaments, where galaxy clusters and groups are concentrated, are dense. The voids between filaments are extraordinarily empty, some spanning hundreds of millions of light-years with almost no galaxies at all. Alcyone sits near the boundary between a filament and a void, in a region where the intergalactic medium density transitions from relatively dense to extremely sparse. Its radiolobes extend preferentially into the void, the path of least resistance. The geometry of the cosmic web itself has shaped the morphology of the largest single structure associated with a galaxy ever measured. This is not unique to Alcyone. A growing catalog of giant radio galaxies, objects whose radio extents exceed 1 megaparsec, or approximately 3.3 million light-years, has been assembled over the past 3 decades from surveys including the LOFAR 2-meter sky survey, the Very Large Array Sky Survey, and the Rapid ASCAP Continuum Survey. LOFAR, the Low Frequency Array, a network of radio antenna stations distributed across Europe and centered in the Netherlands, has been transformative in this catalog's expansion. Operating at frequencies between 10 and 240 megahertz, far lower than most previous radio telescopes, LOFAR is exquisitely sensitive to the faint, diffuse, aged synchrotron emission of old radio galaxy lobes that have expanded and cooled over hundreds of millions of years. Structures that were invisible to earlier instruments are, in LOFAR's data, suddenly apparent. The LOFAR 2-meter sky survey, known as LOTSS, has identified hundreds of giant radio galaxies that were previously uncatalogued. Among them are multiple objects exceeding 5 million light-years in total radio extent. The record, as of the early 2020s, belongs to Alcyone, but the catalog is not finished. LOTSS has currently mapped only a fraction of the northern sky. The southern sky is being surveyed by complementary instruments including MeerKAT in South Africa and ASCAP in Australia. The scientific community's working assumption is that Alcyone will not hold its record indefinitely. What these surveys are collectively revealing is that giant radio galaxies are far more common than previously understood, and that the population extends to scales that the pre-LOFAR era simply could not detect. The universe contains a class of structures, not galaxies in the traditional stellar sense, but galaxy-associated radio structures, whose physical extents exceed those of galaxy clusters, rivaling the scales of galaxy cluster filaments. They are transient features on cosmic timescales. The jets that power them will eventually exhaust the supply of material available for accretion, the lobes will expand and fade, and the radio emission will cool below detectability over hundreds of millions to billions of years. But at any given moment in cosmic history, a population of these objects exists, scattered across the universe's large-scale structure, each one a record of a specific black hole's activity in a specific intergalactic environment over a specific slice of cosmic time. The 2022 Alcyone paper did not merely report a record, it reported a methodology. OE and colleagues developed a rigorous framework for measuring the angular and physical extents of giant radio galaxies from survey data, accounting for projection effects, the fact that a radio galaxy oriented partly along the line of sight will appear smaller in projection than its true physical size, and for the sensitivity limits of the observing instrument. Applying this framework consistently across the LOTSS data revealed that previous catalogs had systematically underestimated the sizes of many giant radio galaxies, because the faint outer regions of their lobes fell below the detection thresholds of the instruments used to catalog them. The true population of extreme radio galaxies is larger, and the sizes of its members are greater than any pre-LOFAR estimate had suggested. Alcyone was the discovery that crystallized this realization. Before it, the record for the largest radio galaxy was held by J 1060 plus 4951, a giant radio galaxy whose radio extent reached approximately 5 million light-years, already extraordinary by the standards of anything previously catalogued. Alcyonius exceeded that by a factor of more than 3. That is not an incremental improvement in measurement precision. That is a qualitative shift in the understanding of what the universe produces. The scientific community's response was measured but unmistakable in its significance. Papers examining the implications of Alcyonius for models of jet propagation, intergalactic medium physics, and large-scale structure appeared within months. The object became a test case. If the standard models of radio galaxy jet dynamics could not accurately reproduce the observed scale of Alcyonius, given its host galaxy's properties and its local environment, then something in those models was incomplete. Early results suggested that the low-density environment was a necessary, but not fully sufficient explanation. The jets of Alcyonius appear to have been active, continuously or episodically, for a period measured in hundreds of millions to perhaps 1 billion years. The lobes are old. The plasma within them has cooled, its radio spectrum steepened by synchrotron aging, telling the story of a black hole that has been quietly, persistently feeding and launching material into the surrounding void across timescales that dwarf the entire history of complex life on Earth. Quiet persistence. In the void. For hundreds of millions of years. The universe's largest known structure associated with a single galaxy was not built in a cataclysm. It was built the way most things in the universe are built, slowly, incrementally, without drama, through the relentless operation of physical law across time. And when astronomers finally had the instrument sensitive enough to see it in its entirety, what they found forced a direct confrontation with a question that the field had been approaching for years without fully articulating. If the universe can produce Alcyonius, if a moderately massive galaxy in a moderately underdense environment, given enough time and the right conditions, can generate a structure 16.3 million light-years across, then what else is out there, in the voids, below the current sensitivity thresholds of every survey we have ever run? The numbers have been building, the scale has been compounding. And now, standing at the edge of what observation and physics together allow us to say with confidence, the full picture assembles itself. Not as a single dramatic revelation, but as the accumulated weight of evidence from radio arrays, X-ray observatories, infrared surveys, gravitational lensing maps, and decades of theoretical refinement, all converging on the same conclusion. The universe builds things larger than any prior framework predicted, and the process is not finished. Alcyonius, at 16.3 million light-years end-to-end, is the largest single structure yet measured in association with an individual galaxy. But it is a radio structure, a product of jet activity, plasma physics, and intergalactic medium density, not a stellar structure in the traditional sense. The question of the largest stellar galaxy, the object containing the most stars, bound gravitationally into a single system, remains a separate and equally compelling problem. These two superlatives do not belong to the same object. The universe, characteristically, has arranged things so that no single record holder dominates every category. The largest stellar galaxies are the BCGs at the centers of the most massive clusters. Objects like IC 1101, like the central galaxy of the Phoenix cluster, like ESO 306-17, a solitary giant elliptical in the southern sky whose extended stellar halo reaches approximately 1.6 million light-years in diameter, and whose intracluster light envelope pushes that figure considerably further. ESO 306-17 is notable for being an isolated BCG. It sits at the center of a moderately rich cluster, but lacks the close companion galaxies that many BCGs possess, suggesting it has already consumed its nearest neighbors, and now feeds primarily on the diffuse intracluster medium and occasional infalling dwarf galaxies. It is, in a meaningful observational sense, the dominant gravitational presence across an enormous volume of space, with no comparable rival within tens of millions of light-years. The Phoenix cluster, formerly designated SPT-CLJ 2344-4243, deserves particular attention. Discovered in 2012 through its signal in the South Pole Telescope's millimeter-wave survey, the Phoenix cluster is the most X-ray luminous galaxy cluster yet detected, containing the hottest and most massive reservoir of intracluster gas known. The gas temperature at its core reaches approximately 15 keV, equivalent to approximately 170 million degrees Celsius. The total mass of the cluster, including dark matter, is estimated at approximately 2.5 times 10 to the 15th solar masses, among the highest cluster masses ever measured. At its center sits a BCG of extraordinary properties. It is forming new stars at a rate of approximately 800 solar masses per year, a figure that is anomalously high for a BCG of its mass and age, and which indicates that the AGN feedback mechanism at this cluster's center is, for reasons still under investigation, temporarily insufficient to suppress the cooling flow. The intracluster gas is condensing and raining down onto the central galaxy at a rate that would, if sustained, dramatically increase the BCG's stellar mass over cosmological timescales. 800 solar masses of new stars per year. The Milky Way, for comparison, forms stars at a rate of approximately 1 to 3 solar masses per year. The Phoenix cluster's central BCG is forming stars somewhere between 250 and 800 times faster than our entire galaxy. This is not a steady-state process. It represents a temporary lapse in the AGN feedback regulation, a window during which the cooling flow is running unchecked, building stellar mass at a rate the BCG will not likely sustain for more than a few 100 million years before the black hole's energy output reasserts control. The black hole at the center of the Phoenix BCG is itself in a state of extreme activity. Its X-ray luminosity places it among the most powerful AGN in the known universe at its redshift, and the cavities it has excavated in the surrounding intracluster gas, imaged by the Chandra X-ray Observatory, are among the largest and most energetic AGN-driven bubbles ever measured. The energy injected into the intracluster medium by a single outburst cycle of this black hole exceeds 10 to the 61 ergs, a number so large it resists direct comparison to anything in human experience. For context, the total energy output of the Sun over its entire 10 billion-year main sequence lifetime is approximately 1.2 times 10 to the 44 ergs. The Phoenix cluster's central black hole releases, in a single episodic outburst, an amount of energy equivalent to roughly 10 quadrillion times the Sun's entire lifetime output. The Sun, its entire lifetime, times 10 quadrillion in a single outburst. This is the regime in which the physics of the universe's largest galaxies operates. Not the gentle stellar physics of main sequence stars and planetary systems, but the extreme relativistic physics of matter compressed to densities beyond nuclear, of magnetic fields measured in millions of Gauss, of plasma heated to temperatures where individual particles move at appreciable fractions of the speed of light. The interior of a BCG's active nucleus is, by any physical measure, the most energetically extreme persistent environment in the observable universe, more energetic than supernovae, more sustained than gamma-ray bursts, operating not for seconds or days, but for hundreds of millions of years. What does this look like observationally? The Chandra X-ray Observatory has been the primary instrument through which the inner workings of BCG nuclei and their surrounding clusters have been mapped. Chandra, launched in 1999 and operating for over 2 decades, images the universe in X-ray wavelengths invisible to human eyes and to optical telescopes. In Chandra's images, the hot intracluster gas of a massive cluster glows with a smooth, extended luminosity. But the smooth surface is deceptive. Within it, the cavities, ripples, shocks, and filaments driven by the central AGN are visible with extraordinary clarity, each one a record of a specific phase in the black hole's activity history. Reading a Chandra image of a massive cluster is, in a precise sense, reading the autobiography of the BCG at its center, a document written in X-ray light across tens of millions of years of cosmic time. The Virgo cluster, the nearest massive galaxy cluster to the Milky Way at approximately 54 million light-years, provides the highest angular resolution view of a BCG nucleus available to current instrumentation. At its center sits M87, Messier 87, an elliptical galaxy of approximately 6.5 trillion solar masses in stellar content, harboring a central black hole of approximately 6.5 billion solar masses. M87 is the galaxy whose central black hole was directly imaged for the first time in April 2019 by the Event Horizon Telescope collaboration. a global network of radio telescopes linked through very long baseline interferometry to function as a single Earth-sized instrument. The image, released simultaneously in multiple cities across the world, showed a bright asymmetric ring of emission, the photon ring produced by light bending around the black hole's event horizon, surrounding a dark central shadow. The shadow's diameter was measured at approximately 42 microarc-seconds, an angular size equivalent to resolving a single donut on the surface of the moon as seen from Earth. That image, the first direct visual confirmation of the shadow of a black hole event horizon, did not merely satisfy a century-old prediction of general relativity. It established M87's black hole as a physical, measurable, spatially resolved object, not a mathematical abstraction. And M87's black hole is not the most massive known. The black hole at the center of TON 618, a hyperluminous quasar located approximately 10.4 billion light-years from Earth, carries a measured mass of approximately 66 billion solar masses, making it one of the most massive black holes yet confirmed by direct reverberation mapping measurements. TON 618 is not a BCG in the cluster center sense. It is a quasar, a phase of extreme AGN activity that dominated the early universe when black holes were accreting at near maximal rates. But its black hole mass establishes the upper range of what the universe's most extreme gravitational objects can achieve. 66 billion solar masses, compressed into a region smaller than our solar system's outer planets. The event horizon of TON 618's black hole, the boundary within which escape velocity exceeds the speed of light, has a Schwarzschild radius of approximately 13 times the distance from the Earth to the Sun. The entire orbit of Saturn around our Sun, the path that Saturn traces over its 29-year orbital period, would fit comfortably inside the event horizon of this object. The event horizon of the black hole at the center of the Milky Way, Sagittarius A star, has a Schwarzschild radius of approximately 12 million kilometers, roughly 1/12 the distance from Earth to the Sun. TON 618's event horizon is approximately 12,000 times larger in radius. These objects, the largest galaxies, the largest radio structures, the most massive black holes, do not exist in isolation from each other. They are connected by the same physical processes: hierarchical merging, AGN feedback, intracluster medium cooling and heating, dark matter halo assembly. The universe's most extreme objects are extreme for the same reason. They have had the right initial conditions, the right environment, and enough time. The physics governing a dwarf galaxy in the local group and the physics governing IC 1101 or Alcyonius are identical. Newton's law of gravitation, Einstein's general relativity, the equations of plasma physics and radiative transfer, the same mathematical framework applies at every scale. What differs is the mass, the time, and the environment. This universality of physical law across 12 orders of magnitude in mass and 16 orders of magnitude in spatial scale is not a convenience. It is the most profound empirical fact in all of science. The universe does not have different rules for different sizes. It has one set of rules applied with perfect consistency everywhere, and the consequences of those rules, applied to slightly different initial conditions across 13.8 billion years, produce objects as radically different as a terrestrial planet and a 16 million light-year radio structure. The largest galaxies are the most extreme expression of a process that began in the first fraction of a second of the universe's existence, in quantum fluctuations smaller than a proton. From that seed, from that infinitesimal variation in energy density, gravity did the rest. Patiently, relentlessly, without any mechanism for stopping, it drew matter together across billions of years, built stars and galaxies and clusters and superclusters, fed black holes until they outweighed entire star clusters, and drove jets of relativistic plasma across distances that make the word large feel like an insult to the concept of scale. Alcyonius is out there right now. Its lobes are expanding slowly at a fraction of the speed of light, pushing into the intergalactic void. The plasma within them is cooling. The electrons are losing energy, their synchrotron emission shifting to lower and lower frequencies, eventually fading below the detection threshold of any instrument we have yet built. In a billion years, perhaps 2, Alcyonius will be invisible. The record it currently holds will belong to something else, something that may already exist in a void somewhere in the observable universe, its aged lobes too faint to see with current technology, waiting for an instrument sensitive enough to find it. The observable universe contains 2 trillion galaxies. LOFAR has surveyed a fraction of the northern sky. The southern hemisphere surveys are incomplete. The low-frequency radio universe, the regime in which the oldest, most extended, most faded radio structures are detectable, has barely been explored. Every square degree of sky that a sufficiently sensitive radio telescope examines for the first time is a square degree that has never been examined before. The record will fall again. The question is not whether. The question is by how much. There is a photograph taken by the Voyager 1 spacecraft on February 14, 1990. At the request of Carl Sagan, NASA commanded the probe, then approximately 6 billion kilometers from Earth, having just crossed the orbit of Neptune on its way out of the solar system, to turn its camera back toward the inner solar system and take a portrait. In the resulting image, Earth appears as a pale blue dot, less than a single pixel in size, suspended in a beam of scattered sunlight against the absolute black of interplanetary space. Sagan described it as a mote of dust suspended in a sunbeam. The description was precise. It was not metaphor. That photograph was taken from within our solar system, not from the edge of our galaxy, not from the neighboring galaxy, not from the local group boundary, from within our own solar system, a distance so trivially small by the standards of the structures documented in this film that it does not register on any scale useful for discussing the objects we have been examining. The Milky Way, in which that photograph was taken, spans 100,000 light-years. Light traveling at 300,000 kilometers per second would take 100,000 years to cross it. Voyager 1, moving at approximately 17 kilometers per second, would take approximately 1.7 billion years to cross the Milky Way, assuming it traveled in a straight line, which it does not. Voyager 1 has been traveling since 1977. It has covered approximately 23 billion kilometers. The Milky Way is 950 quadrillion kilometers wide. Voyager 1 has covered approximately 0.0000024% of the Milky Way's diameter in nearly 50 years of continuous travel. And the Milky Way, as established at the very beginning of this examination, is not large. IC 1101 is 60 times the diameter of the Milky Way. Alcyonius, end to end, is 163 times the diameter of the Milky Way. The observable universe, the sphere of space from which light has had enough time to reach us since the Big Bang, is approximately 93 billion light-years in diameter. The observable universe contains an estimated 2 trillion galaxies. The total number of stars in the observable universe is estimated at approximately 2 times 10 to the 23rd power. A number that exceeds, by several orders of magnitude, every grain of sand on every beach and desert on the surface of the Earth. These are not rhetorical flourishes, they are measurements. What does it mean, physically and scientifically, to stand inside a universe of this scale? The question is not philosophical decoration. It is a direct consequence of the observational record. Every measurement described in this documentary, every redshift, every angular diameter, every X-ray luminosity, every radio flux density, was made by instruments designed and built by a species whose entire evolutionary history unfolded on a single rocky planet, orbiting an unremarkable star in the outer region of a mid-sized spiral galaxy that sits in a relatively sparse corner of the local group, itself a minor gravitational node in the Virgo supercluster, itself a component of the Laniakea supercluster, a structure 520 million light-years across containing the mass of approximately 10 to the 17th solar masses, first fully mapped in 2014 by Brent Tully and colleagues using Galaxy peculiar velocity data. Laniakea. The name comes from Hawaiian, meaning immeasurable heaven. The astronomers who named it chose deliberately. Our supercluster, the structure within which the Milky Way resides, is itself dwarfed by the filaments of the cosmic web, themselves dwarfed by the full extent of the observable universe. The hierarchy does not bottom out at a comfortable level. It does not arrive at a scale where human beings are central, significant, or even particularly notable as physical objects. The physical universe, read empirically and without any obligation to comfort, is a structure in which the matter constituting all stars, planets, and living organisms, the baryonic matter measured and catalogued by every telescope ever built, accounts for approximately 5% of the total energy content of the observable universe. Dark matter accounts for approximately 27%. Dark energy, the poorly understood component responsible for the accelerating expansion of space, accounts for the remaining 68%. The stuff of which we are made, and of which every galaxy ever observed is made, is a minor constituent of a universe whose dominant components we cannot directly detect. This is the cosmological context in which the largest galaxies exist. They are the most extreme concentrations of that 5%, the most massive, most extended, most gravitationally dominant accumulations of baryonic matter and dark matter halos in the observable universe, and they are still only tracers. The dark matter halos surrounding even the most massive BCGs extend into a component of the universe that does not emit, absorb, or reflect light by any mechanism currently understood. The full gravitational mass of these objects, the true extent of their influence on the surrounding universe, is not visible. It is inferred. The scientific method, applied to this problem across the course of a century, has produced a picture of the universe that is simultaneously more ordered and more strange than any prior framework anticipated. More ordered because the same physical laws, gravity, electromagnetism, the strong and weak nuclear forces, quantum mechanics, general relativity, apply with extraordinary precision at every scale, from subatomic particles to the large-scale structure of the observable universe. The mathematics works. The predictions match the observations to a degree of precision that is, by any historical standard, remarkable. More strange because the universe those laws describe is one in which most of the matter is invisible. Most of the energy is accelerating the expansion of space in ways that general relativity did not predict without modification. And the structures that emerge from the application of those laws at cosmological scales are so extreme that they fundamentally resist intuitive comprehension. IC 1101 contains 100 trillion stars. That number is not graspable by the human mind in any direct sense. The human brain evolved to count objects in the tens and hundreds, to navigate spaces measured in meters and kilometers, to plan across timescales of years and decades. It did not evolve to hold 100 trillion of anything. The tools that allow us to make contact with that number, mathematics, physics, telescope instrumentation, computational simulation, are themselves products of the same biological substrate that cannot intuitively process it. The gap between what the universe is and what the human brain can directly experience is not a failure of science. It is a precise measurement of the difference in scale between a conscious organism and the cosmos in which that organism exists. And yet the measurement was made by human beings, with instruments human beings designed, built, and operated. The data that established the diameter of Alcyonius, the mass of TON 618's black hole, the star formation rate of the Phoenix cluster's BCG, the sound waves propagating through the Perseus cluster's intra-cluster medium, all of it was extracted from the universe by a species that has been technologically capable of doing so for, at most, a few hundred years. In the context of the 13.8 billion-year history of the universe, the entire period of human scientific observation is not a rounding error. It is invisible. The largest galaxy-associated structure ever measured, Alcyonius, at 16.3 million light-years, has been expanding its radiolobes for longer than complex multicellular life has existed on Earth. The universe was already producing structures of that scale before the Cambrian explosion, before the first fish, before the first land plant, before the first dinosaur, before the first primate. The physical processes that built Alcyonius were operating according to precisely the same laws we use to describe them today, in a universe that had not yet produced anything capable of noticing. The noticing happened very recently, by a very small species, on a very small planet, at the edge of a very ordinary galaxy. That the noticing happened at all is not guaranteed by physics. The laws of the universe do not require the existence of observers. General relativity does not include a term for curiosity. The Boltzmann equation does not have a variable for wonder. The formation of a species capable of measuring the universe is not a predicted output of the standard cosmological model. It is a contingent fact, a product of a specific evolutionary history on a specific planet, the result of billions of years of biological trial and error under specific local conditions, producing, among other things, the neural architecture required to ask questions about things that have no direct bearing on survival. The questions exist anyway. The measurements exist anyway. The 2 trillion galaxies exist whether or not anyone measures them. YC1101's 100 trillion stars were burning before any eye existed to see them. Alcyonius's lobes were expanding into the intergalactic void before any mind existed to calculate their extent. The Phoenix Cluster's BCG was forming 800 solar masses of new stars per year before any instrument existed to detect the light. The universe is indifferent to its own observation. It runs according to its laws regardless, but the observation changes something, not in the universe, which does not register it, but in the observer, who is now in possession of a picture of reality that is larger, stranger, older, and more precisely described than any framework that preceded it. The largest galaxies are not endpoints, they are current measurements. Every figure cited in this documentary carries an implicit asterisk. As of the most recent survey, with the most sensitive instruments currently available to the precision currently achievable. The record for the largest known radio galaxy will fall again, because the surveys are incomplete. The measurement of dark matter halo extents will improve, because the instruments are improving. The understanding of AGN feedback, intracluster medium physics, and the upper mass limit of galaxy-scale structures will deepen, because the questions are unresolved and the community is working. The Vera C. Rubin Observatory in Chile, which began its legacy survey of space and time in 2025, will image the southern sky with unprecedented depth and cadence over a 10-year baseline, producing a catalog of galaxies and galaxy clusters that will dwarf every prior optical survey in scale and sensitivity. The Square Kilometre Array, the SKA, currently under construction in South Africa and Australia, will, when complete, be the largest and most sensitive radio telescope ever built, capable of detecting radio emission from galaxy structures at distances and surface brightness levels entirely beyond the reach of current instruments. Whatever Alcyonius's successor in the record books turns out to be, the SKA is among the most likely instruments to find it. The universe is not finished being measured. It is not finished being understood, and it is not finished building things. Somewhere in the observable universe, right now, in a void between filaments of the cosmic web, a supermassive black hole is driving relativistic jets through almost empty intergalactic space. The jets have been running for a long time. The surrounding medium is thin. There is nothing to stop them. They are expanding outward, carrying with them the energy of one of the most extreme physical processes in the known universe, into a region of space so empty that no current instrument is sensitive enough to detect their emission. They will continue expanding. The universe will continue running according to its laws. At some point, perhaps decades from now, perhaps a century, an instrument will be built that is sensitive enough to see them. A team of researchers will examine the data. The numbers will be cross-checked, the measurements will be verified, and the largest known structure associated with a single galaxy will be larger than Alcyonius. The universe does not wait for permission.